Alright, hi guys. I've got the Maths Methods Exam 1 2024 Northern Hemisphere here. I've taken a look through it, but I haven't actually had a go at it yet. It doesn't look too bad, so we're going to give it a crack and see how we go. So let's get started. Like always, question 1 is just finding a derivative. Here it actually says find and factorize, so we'll actually need to factorize our answer. But let's find dy dx. So we've got a product here, product of two functions, so let's use the product rule, left d right, and then right d left. So x, and then the derivative of e to the x squared plus 1. And then the derivative of x is just 1 times e to the x squared plus 1. We can simplify this a little bit. And as instructed, we need to factorize, so we'll factor out e to the x squared plus 1. 2x squared plus 1, and that should be that. Part B, we've got f of x equals a quotient this time, so we use the quotient rule. Evaluate f dash x at x equals e. So this is typical of part B's, that you need to find f dash x, and then don't forget to sub in the value you've been given for the second mark. If you can't remember your quotient rule, I remember it as just derive the top one first and then the bottom one. But if you can't remember your quotient rule, you can just grab the formula from the back of the exam. That's what I'm doing now. And you can use that. Okay, f dash x equals derivative of x cubed is 3x squared times ln x unchanged, and then minus the derivative of ln x is just 1 on x times x cubed. Now all over our denominator squared. So ln x squared. And take note, it's not ln of x squared, it's the entire term ln x, all squared. We can simplify this a little bit, so 1 on x times x cubed is just going to be x squared. And seeing as we're going to be putting in e for x, we could factorize the x squared, might make things a little bit easier. Okay, f dash e. I'll do it down here. Now we know this ln e is going to simplify to 1. And the same is going to be true of ln e in our denominator. So of e squared, and then 3 times 1 is 3, minus 1 is 2, so 3 minus 1 is 2, over 1 squared. So this is 2e squared. Question 2. Consider the simultaneous linear equations where a belongs to r. Let's underline that. Find the value of a for which there are infinitely many solutions. Okay, so there's a lot of different ways of doing this. The way I prefer is just to rearrange the equations into the form y equals mx plus c. It's not the fastest way, but I like it because you can kind of see what's going on with the gradients and the y-intercepts very clearly and very intuitively. So I'm just going to rearrange these two equations, moving the ax over to the other side first, and then dividing both sides by 2 minus a. Dividing the 3 by 2 minus a as well, and that's my first equation. For this x plus ay, let's move the x over to the other side. And divide everything by a. Okay, we want infinitely many solutions, which means we need the gradients to be the same, and also the y-intercepts to be the same. So let's start by equating the gradients. Negative a on 2 minus a has to be equal to negative 1 on a. The negatives will cancel. The a and the a, well, let's cross multiply the a's. So we get a squared and cross multiply the 2 minus 1 times 1, 2 minus a times 1 rather, 2 minus a. Let's bring everything to one side. Factorize. We'll have minus 1 plus 2. Therefore, a equals minus 2 or a equals 1. So those are the gradients. Let's tackle the y-intercepts. Let's equate those. 3 on 2 minus a must equal 2a plus 1 on 2a. Cross multiplying again. Collecting like terms. 4a minus a is 3a. And bringing it all to one side. Let's put a plus 2 here and a minus 1 there. Therefore, a equals 1/2 or a equals negative 2. Now we need the intersection of these two sets of solutions because we need both the gradients to be equal and the y-intercepts to be equal simultaneously so that the graphs basically superimpose on top of each other and have infinitely many solutions. So where are these the same? Well, a equals negative 2 and a equals negative 2. So that's our answer. Find the values of a for which there is a unique solution. Values of a, whereas this one said value of a. So that's good that we found only one value. Here we're going to be looking for more than one value, so the set of values. Now a unique solution, we're going to want the gradients to not be equal to each other, because if they're equal to each other, as we saw here, then we get infinitely many solutions or we get no solutions. So it should just be r except negative 2 or 1 are our values for a. Let's consider some special cases though. So looking at our original equations, what happens if a equals 2? You can see this bit here, 2 minus a lots of y. So if a equals 2, this becomes 0. This becomes 2x equals 3. And this becomes x plus 2y equals 5 on 2. So this one is a vertical line. This one is still a sloped line, which means that we still will have a unique solution. So this is fine. The other thing to consider would probably be letting a equals 0, because that's going to kind of delete this term here. So when a equals 0, we'll have, well, that's 0 here, 2 minus 0. So we have 2y equals 3 for this first equation, which leads to y equals 3 on 2. And if we were a equals 0 here, we have x equals 1/2. So we have a horizontal line and a vertical line, perpendicular to each other, which is still a unique solution. So all these special cases are fine. So that's our answer here. Find a value of a value of a. So that implies that there's more than one possible value, but we just need one of them, because otherwise it would have said find the value of a, like it did in part A. Find a value of a such that the lines meet at right angles. Okay, so we just found one case there. When a equals 0, we get that the lines are perpendicular to each other because one of them is a horizontal line and one of them is a vertical line. So we could say a equals 0 would be our answer. Now, probably the more typical way of approaching this question, perhaps finding one of the other solutions, would be to say that if they meet at right angles, if they're perpendicular, then the product of their gradients is -1. So the first gradient is negative a over 2 minus a, times the second gradient is -1 on a. This has to equal -1. Let's solve this for a. So we're going to have negative times a negative is a positive, a, and then times over a, they're going to cancel. We're going to end up with 1 on 2 minus a equals -1. 1 equals a minus 2. Therefore, a equals 3. would be another solution. Because it says a value, either of these solutions should be fine. Question 3, we've got a log function with domain of D, where D is the domain for f. Yep. State the maximal domain for f of x. Okay, so we need the contents of the log here to be greater than 0. So we'll have 2 minus x is greater than 0. Let's bring the x to the other side. We could bring the 2 to the other side and then divide. We just need to remember to flip the sign. So 2 is greater than x, which means x is less than 2. So the maximal domain for f, D, it doesn't actually say if D is the maximal domain. I think that's what they meant. I'm just going to say maximal domain of f is negative infinity to 2. Round brackets because we can't have 2 in here, otherwise we'd have ln of 0. Sketch the graph of f, labeling the asymptote of its equation and the axial intercepts with their coordinates. Okay, so we could take this equation here, and if you want to, if it helps you visualize, you could rewrite it to show the transformations compared to the graph of ln x. So this would be 3 ln, and we could factor out the negative here. So we could have minus and then x minus 2. And this kind of shows us that there's a reflection in the y-axis and that there's a translation 2 units to the right of our asymptote, or of the entire function including the asymptote. So our asymptote, as expected, is at x equals 2. And let's not forget the reflection in the y-axis. We need to label the asymptote, which we've done, and the axial intercepts with their coordinates. So before we sketch, let's actually find the intercepts to guide us. So f of 0 for our y-axis, 3 ln of 2, and let's solve f of x equals 0 for our x-axis, x-intercept. Dividing both sides by 3, 0 equals ln 2 minus x. Now we know that ln of 1 is 0, so we would have ln of 2 minus 1 is ln 1, so therefore x equals 1. Okay, so 1 for our x-intercept is halfway between 0 and 2, so here. And now 3 ln 2 is our y-intercept. We know that E is approximately 2.718, so approximately 2.7, which is bigger than 2, so the base of the log is bigger than the contents of the log. So ln of 2 is something that's a bit less than 1, something about 0.7-ish. So 3 times that is something that's about 2.1-ish. So if we're going to get the scale right here, and it's a little bit unusual that they haven't given us grid lines, but just roughly, we're going to have a bit more than 2 times this up here if we want things to be scaled correctly for the x and y axis. So something like this is about 2.1. This makes sense with our reflection. And let's make sure that we're kind of approaching that. Let's do that again. Approaching that asymptote without kind of bouncing off of it. Okay, have we got everything? Label the asymptotes? Yes. Label the axial intercepts with their coordinates? Yes. 3 marks, probably 1 for this, this, and this, and shape. Find the values of x for which 0 is less than or equal to the function f of x is less than or equal to 3, so the value of the function itself. Okay, whenever you're doing these inequalities, it is really helpful to have the graph, so it's good that we've drawn the graph first, because the graph can actually guide us. We're looking for the value of the function is between 0 to 3. So we know the value of the function is 0 at our x-intercept, and then we're thinking this part of the function here, as the function gets higher, until it hits some value of 3. And we know, like we were talking about before, that this value is approximately 2.1-ish, or a little bit more than 2. So 3 is about here, which means that we have a lower bound of some slightly negative x value. So let's solve for what value of x does the function actually equal 3, and that'll be our kind of lower bound. The function was 3 ln 2 minus x. when is that equal to 3? Two minus x equals e to the 1, which is just e. So x equals 2 minus e. And that also makes sense because e is 2.7-ish, so 2 minus 2.7 is approximately negative 0.7, which is kind of where we were expecting to get our value of 3 for the function. So that's our lower bound. So x belongs to 2 minus e, and it's a less than or equal to, so we'll include that with a square bracket. And then our upper bound, well, that was that. Our upper bound was this x-intercept here. That's where the value of the function is 0, and that was at an x value of 1. Okay. Question 4. We've got a log function and an exponential function. The exponential function's domain is R. The log function is from 3 on 2 to infinity. And we've got composite functions, g of h. So h will be the inner function, the exponential. Show that g of h is defined for all x belongs to R. Okay, if we do a quick sketch of h, we've got the +2 translation, so we've got a horizontal asymptote at y equals 2. And the graph looks something like this as an increasing function. So this is h of x. So we know range of h, as seen from the graph, is from 2 to infinity. Domain of g, we're told, is 3 on 2 to infinity. Now we know that 2 to infinity is a subset of 3 on 2 to infinity. So therefore, the range of h is a subset of the domain of g. And this is for x belongs to R. So therefore, g of h is defined for x belongs to R. I think that's all they wanted there. Find the range of g of h given the domain of g of h is x belongs to R, which is what we just said it is. Okay, so there's two ways of doing this, two kind of methods. I'll talk about the one that I don't prefer first, and then I'll show you the one that I prefer. So the one that I don't really like too much is just going ahead and finding g of h. So h is the inner function, put this function inside the log function. So you get log e and then 2 times this, and then minus 3. Simplify that, and then consider the domain x to R, x belongs to R, going into that composite function, and consider the behavior of the function and the range that you get out across the entire set of values x belongs to R, and that'll be your range of your composite function. Now the way I prefer is to instead think of the inner function's range. So the range of h we've already found was 2 to infinity. And because this is the inner function, it's going into g, we have g of h. This is going to be the set of inputs that goes into the function g. So instead of considering the rule for the function g of h, let's just consider the rule of the function g, and we'll just be putting these inputs into it, which are the outputs of h. So g of x, so consider inputs of 2 to infinity, which was our outputs of h, our range of h, into g, which was ln 2x minus 3. Okay, so when we put 2 into ln 2x minus 3, well, we can't actually sub 2 in because it's a round bracket, but as x approaches 2 from the right, so as we have 2.000001, as we approach 2 from the right, and we sub it into ln 2x minus 3, or as we think of the value of that function, as we approach an x value of 2, it's going to be approaching ln 1 from the right, so approaching 0. G approaches 0. And as x approaches infinity, our upper bound, well, we'll have ln of 2 times infinity minus 3. This thing it's an increasing function. It's heading towards a value of infinity for g. So g approaches infinity. So therefore, the range of the composite function g of h is round brackets because we were only approaching this value because we couldn't sub 2 in. 0 to infinity. So hopefully that method makes sense. If you're one of my current students and that doesn't make sense, let me know and we'll go through it again because we have gone through this in the past and I think it's a good method to use here. Okay, so we've got some statistical inference here. In a nursery, 90% of the seeds will grow into seedlings, where p happy the random variable representing the sample proportion of seeds that will grow into seedlings for samples of size 100. So we've got p equals 90%, or 0.9, and we've got n equals 100. Find the mean and standard deviation of p hat. Okay, so the mean, e of p hat, is just going to be that 0.9, or 90%. And the standard deviation, so we can find the variance and then square root it, or we can just grab the formula from the formula sheet at the back of the exam, if I can find it. There it is. And let's calculate this standard deviation. So the square root of p, which is 0.9, I might express this as 9/10, and then times 1 minus p is 1/10, all over n, which is 100. So we get the square root. Now 9/10 times 1/10 is 9 on 100, all over 100. Square root of 9 is 3. Square root of 100 is 10 over, and then the square root of this 100 in the denominator is also 10. 3 over 10 times 10 is 3 over 100, or 0.03. Does that seem sensible? With p being 0.9 and n being 100, yes it does. Seems fine to me. Let z be the standard normal random variable such that z is the standard normal variable, 0, 1. And the probability z is greater than -1 is approximately 0.84. Using a normal approximation of p hat, estimate the probability that a sample of 100 more than 93 seeds will grow into seedlings. Give your answer correct to 2 decimal places. So we know n equals 100. We want the probability of more than 93 will grow into seedlings. And the mean for the distribution for the... We can expect 90 seedlings. 90 seeds to grow into seedlings. So that's this 0.9 times the 100 will be 90 of the 100 seedlings. And then the standard deviation for the population parameter is 0.03. I'm going to work with 3 as so just the 0.03 times 100. So in terms of the actual seedlings, we're expecting 90, and then standard deviation of 3. So we could say something like x is distributed normally with a mean of 90 and a variance of 3 squared. So the probability that x is greater than 93, more than 93 seeds, okay, we're told that the probability z is greater than -1 is this. So here's -1, 1 standard deviation to the left, and greater than that is all this section here. This is 0.84. And we have 1 standard deviation to the right, so if this is 90, this is 93, and we want greater than that, so that's this bit here. That's what we want, that probability there. So you can kind of see that this is the equivalent, it's one standard deviation greater than, so it's the equivalent on the standard norm of greater than 1. These are the same areas because they're both one standard deviation greater than the mean. And this is, by symmetry of the normal distribution, this is equal to this unshaded region here, and that's 1 minus 0.84 is 0.16, 0.16, 0.16. So to 2 decimal places, 0.16. Not sure how big of a fan I am of to 2 decimal places when we've got an approximate that we're using in our working, but oh well. Okay, we've got a sine function translated 2 units up, shown below, using the trapezium rule. Approximation method and 3 trapeziums of equal width estimate the area bound by the graph of y equals g of x, the x-axis, and the lines pi equals 6 and x equals 2 pi on 3. Okay, so we're going from here to here. Let's split this up using 3 trapeziums. So here's our first one. Here's our second. And here's our third. Not even OneNote will recognize my trapeziums, they're that bad. Let's do that again. Actually, that'll do like that. Okay. So, if you've forgotten it, the formula for the trapezium estimation is on the formula sheet. So I'm going to grab that now. And actually, you can see they've chosen really nice numbers for us. So these exact values that we're familiar with for the trig function, and they correspond to these values here. So let's actually just grab these points. So this is what, pi on 6, 1, pi on 3, 1.5, which is 3 on 2. So I'm doing this so I don't have to think about them later when I sub it all into this mess of a formula. Pi on 2, 5 on 2, and 2 pi on 3, 3. Okay, xn minus x0, so the largest one is 2 pi on 3. And then minus x0 is where we start at pi on 6. Over 2n, where n is the number of trapezoids, so 2 times 3 is 6. All times, now the value of the function at f0, so that is f of pi on 6, which as we can just see from here, is just 1. So 1, and then plus 2 times the value of f at pi on 3 is 3 on 2. Plus 2 times the value here, which is 2 times 5 on 2. And then plus 1 times our last value of the function at f of 2 pi on 3 is 3. And that should be it. So keep in mind that only the first and the last is just 1 times, and all the other ones in the middle are 2 times the value of the function at that point. Okay, 2 pi on 3 minus pi on 6, so that's pi on 2. Pi on 2 over 6 is pi on 12. We have 1 plus 3 plus 5 plus 3 is 12. 12 pi on 12 equals pi. Equals pi. Oh. Yeah, this is actually quite nice, because usually the trapezium method gives us a decent estimation, but it won't give us the exact area. In this case, this is the exact area, but you can see we start at the trough and we go to the peak, and for this first trapezium, we get kind of an overestimation of this bit here, but that's cancelled out by the underestimation in our third trapezium of this section here. So these two kind of cancel each other out. And then this bit here, you can, if you zoomed in enough on the curve, you'd see it's got some smooth curvature. It's not a straight line like I've drawn for my trapezium. And there's a little bit that we're underestimating here, and then a little bit that we're overestimating here that cancel each other out because of the symmetry at the point of inflection here. So we end up with each of the trapeziums might not be a perfect estimation, but the overall thing is actually equal to the exact area of 1 pi. Okay, so in part B, we've got h of x, which now has a domain, and it is k times g of x, so some dilation factor from the x-axis that's going to be affecting our function g, not just the sine part, but also the plus 2 part, dilating it from the x-axis, where k belongs to r. Using calculus, find k such that h is a probability density function. So for a probability density function, we're after two things. Firstly, that it's non-negative, so it all has to be equal to or above the x-axis, because the area under the curve represents the probability, and if we have a signed negative area, that would represent negative probability, which doesn't make a lot of sense. And then the second thing, which is probably more important for this question, is that the area from negative pi on 6 to 2 pi on 3 under the curve should equal 1, because the sum of all probabilities is 1. So we're going to integrate from pi on 6 to 2 pi on 3, k times g of x, and that should equal to 1. K times g of x, where g of x was this sine function. So what we'll do, because the k has to apply to the entire function, let's just factor it out. K is just some number. Sine 2x minus 5 pi on 6. And then plus 2. And don't forget your dx, sad way to lose a mark. And this should be equal to 1, because the area underneath the probability density function should be 1. Okay, let's find the antiderivative. Antiderivative of sine is negative cosine. And we'll need to divide by this coefficient of x here. So negative 1/2 cos 2x minus 5 pi on 6. Plus this 2 will become 2x is equal to, with terminals of pi on 6 and 2 pi on 3 is equal to 1 on k. I've just divided both sides by the k here because I don't want to kind of have nested brackets where the k has to apply to every set of brackets when I sub these values in. Speaking of, let's sub these values in. So we're going to have negative 1/2 cosine of 2 times 2 pi on 3 is 4 pi on 3. Minus 5 pi on 6. 4 pi on 3 is 8 pi on 6. Minus 5 pi on 6 is 3 pi on 6, which is pi on 2. Plus 2 times 2 pi on 3 is 4 pi on 3. Minus, let's sub this one in. Negative 1/2 cosine. 2 times pi on 6 is 2 pi on 6. Minus 5 pi on 6 is negative pi on 2. And then plus 2 times pi on 6 is pi on 3. Is equal to 1 on k. Okay, negative 1/2. So cosine of pi on 2, think of your unit circle or your exact values. Cosine of pi on 2 is 0. So this is just going to be 0 plus 4 pi on 3 minus cosine of negative pi on 2 is also 0. So 0 plus pi on 3 equals 1 on k. And we'll have 4 pi on 3 minus pi on 3 is 3 pi on 3, or pi, equals 1 on k. Therefore, k equals 1 on pi. Okay, so it's very easy to make a mistake when you're doing a whole bunch of integration. So setting things out in a way that you're used to, that makes logical sense for you, is really good. And also, if there's any way that you can kind of check your answer or see that the direction you're heading in makes sense, that's really good too. So with our trapezium estimate, we found that this area was pi, and we need this area to be 1 after we scale it by the dilation factor k. So if we need this area to go from pi to 1, then the dilation that we're going to do from the x-axis is we're actually going to squish it down. So we're going to multiply by 1 on pi, because then pi area times 1 on pi will give us an area of 1, which is what we need for the probability density function. So hence our dilation factor is 1 on pi, and we can be confident that this answer is correct. Reasonably confident anyway. I am a little bit surprised this is only 2 marks. This is a lot of work. We could have just used our estimate from the trapezium method, except that it says using calculus. So I do think we had to do all this integration, which was a lot of work. Question 7, we've got a discrete random variable x with a probability mass function. So it's a mass function because it's a discrete variable. It would be a density function for a continuous variable like this one here. Of probability x equals 2 on 3 to the x, where x is a positive integer. So this is like a geometric series. So this is kind of specialist. Okay, find probability x equals 4. So we'll just sub 4 in here. So the probability that x equals 4 equals 2 on 3 to the 4, which is 2 on, well, 3 squared is 9, 3 squared is 9 squared, 81. Index was 2 on 81. Find the probability x is less than 4 given x is greater than or equal to 2. Let's make a table here. So we've got x and the probability that x equals x. We got 0. Sorry, we don't have 0 because it's z plus. So positive integers, which doesn't include 0. 0 is not a positive integer. It wouldn't make much sense to put in a 0 here anyway. And have a probability of 2. That would be obviously too big. So 1 is our first value. 2, 3, 4, and so on. So when we sub x equals 1 in, we get 2/3. 2 on 3 squared is 2 ninths. 2 on 27, we've already seen this one is 2 on 81, and so on. And the sum of all of these would be 1. Now, find the probability that x is less than 4, given x is greater than or equal to 2, so a conditional probability, we need to find the intersection of these two things. So the intersection of less than 4, keep in mind this isn't continuous, this is discrete, so less than 4 means 3 or less. And then intersecting with greater than or equal to 2 is 2 or greater, so that'll be 2 to 3. So 2 is less than or equal to x is less than or equal to 3 over the probability x is greater than or equal to 2. Be careful of symmetry that you might expect here. It's a little bit different to usual, because say you wanted to find the probability that x equals 4, which we've already done, but if you wanted to find it using symmetry or something like that, you might think it's the complement to just this part here. So you might say 1 minus this, but it's not, because remember there's infinitely many more terms here. So be careful with the symmetry here. Okay, between 2 and 3, so 2 plus 3, 2 on 9 plus 2 on 27. 2 on 9 is the same thing as 6 on 27, so that's going to be 8 on 27. Greater than or equal to 2, so that's all of this. So here we actually can use the complement, because it's going to be 1 minus everything else, so 2/3. 1 minus 2/3. Because the probability that x equals 1 is 2/3, so the probability x is greater than or equal to 2 is all of this, or 1 minus 2/3. So that's going to be 1/3. Fraction divided by another fraction, you can have fraction multiplied by the reciprocal. So 8 on 27 times 3 on 1 would be one way to do this. 8 on 1 is 8, and 3 on 27 simplifies to a denominator of 9, 8 ninths. That seems reasonable. Question 8 out of 9. This is feeling like a bit of a long one. Okay, we've got a function here. Find an antiderivative for f of x. Sure. So we can express this as 3x plus 1 to the power of -1/2. dx. We'll raise this power by 1, making it positive 1/2, and then we'll divide by the new power. Dividing by 1/2 is the same thing as multiplying by 2. So we'll have 2 times, and then let's also not forget to divide by the coefficient of x in here. So 2 on 3 times the square root, because we'll have this to the power of 1/2, which is the square root, 3x plus 1 plus c. So let's just double check that, because this is easy to kind of forget or slip up. We need to divide by the coefficient here, that's the over 3. We need to raise the power by 1, which takes it to 1/2, and then divide by that 1/2 is the same thing as multiplying by 2. And then the new power is 1/2, so that's the same thing as square root. Okay, it looks good. Now it says an antiderivative, so we can say therefore 2 over 3 square root 3x plus 1 is our value, is our example of an antiderivative. We could even say where c is chosen to be 0 in our example. Okay, the average value of the function f between 0 and m is 1/3. Find the value of m. So our average value is going to be 1 on m minus 0. And we could think of this as dividing by the width of the function to find the average value, because we're multiplying by the reciprocal of the width. So we're going to integrate from 0 to m, lower bound to upper bound, of our function f of x dx, and this should be equal to our average value of 1/3. We've already done this antiderivative, so let's just grab that from above. And let's actually factor out the 2/3, which might make things a little bit easier to evaluate here. So we have 1 on m, and then times 2/3, we'll have 2 on 3m, and then square root of 3x plus 1 from 0 to m equals 1/3. Okay, 2 on 3m, subbing in m here, 3m plus 1. And then we'll have minus, subbing in 0 here, will not make this 0, it'll make it the square root of 1, which is 1. Still equals 1/3. Let's multiply both sides by 3m, so we'll have 2 square root of 3m plus 1 minus 1 equals 3m on 3, which is just m. Expanding the left-hand side, 2 square roots 3m plus 1 minus 2 equals m. Bringing the 2 to the other side, m plus 2. And let's square both sides now, because we need to get rid of this square root here. So we'll have 4 3m plus 1 equals m plus 2 squared. We do need to be careful of checking our solutions, making sure they're both valid, that we haven't introduced any invalid solutions when we've squared both sides here. So we'll do that at the end. Expanding, 12m plus 4 equals m squared plus 4m plus 4. M squared minus 8m equals 0. Factorize out a common factor of m. M minus 8 equals 0. Therefore, m equals 0, or m equals 8. Okay, so 8 seems fine, but 0 does not, because this is the average value of the function is 1/3 when we integrate from 0 to m. If m is 0, then there kind of isn't a function, it's just a single point. An average value of the function, well, the function as a set of ordered pairs kind of implies that it's more than one point, so I believe we'd get rid of this. We'd reject this m equals 0 solution. We'd say m is greater than 0, therefore m equals 8 is our answer. It does say find the value of m. Okay, last question. We've got f of x equals x minus 1 times e to the negative x. Find the derivative. Okay, so this is just going to be the product rule. So left to right, right to left. We'll have x minus 1, and then the derivative of e to the negative x is just going to be negative e to the negative x, plus derivative of all this is just 1 times e to the negative x. Let's neaten this up a little bit. Kind of come full circle here. This is kind of what we started with in question 1a, taking out the common factor of the exponential. So e to the negative x, x minus 1, is that one there? Sorry, it's a minus, so minus x minus 1 plus 1, which we can then simplify, e to the negative x, 2 minus x. Or we can write 2 minus x times e to the negative x to put the polynomial bit first. Okay. State a sequence of transformations that will map f onto its derivative, so this onto this. So what I'm going to do is just rearrange this by factoring out the negative 1 here, so I can kind of compare what's going on with the x's. So this is just the same thing as negative x minus 2 e to the negative x. So now it looks a bit more like this, so it should be easier to see the transformations we need to apply. And yeah, you can kind of see that, you can see more clearly now that we just need to multiply this thing by negative 1 for our first transformation, so that is a reflection in the x-axis. So that takes this and it makes it negative x minus 1 e to the negative x, so we're kind of one step closer. We just need to get to this 2 now, so that's going to be a translation of 1 unit to the right. One unit right, which will take us to x, and then we'll replace x with x minus 1. X minus 1 minus 1 will become x minus 2 like we needed. So we do have a problem here. We might need to do a reflection in the y instead. So the problem I'm seeing here is, well, you've got to get this minus 1 to become a minus 2, but we need this minus x to stay a minus x, not become an x minus 1. Oh, yeah, we can, let's do exactly what we've done. Let's expand this. So this equals negative x minus 2 e to the negative x plus 1, and then let's split this up. E to the negative x, so e to the negative x plus 1 is the same thing as e to the negative x, and then times e to the 1. So your very first index of what you ever learned, these are equivalent. And now we can see that we can just scale this thing by 1 on e, so a dilation from the x-axis. By a factor of 1 on e. So this bit is the answer, this is just my working, because if we take this and we multiply it by 1 on e, it will cancel with the e to the 1, leaving us with just this, which is our derivative that we wanted. That is a tricky question. Hopefully that's right. Show that the derivative of this is equal to f of x. Product rule once again. Let's factor out the e to the negative x. which is our original f of x, as we expected. Okay, I was having a look at this one before. Let y equals g of x be the tangent to y equals f of x at the point 3, f of 3. So here's our curve f of x here, and then we've got this tangent g of x. And then it says using the derivative that we just found before is equal to f of x. So kind of like an integration by recognition question. Or otherwise, determine the area of the region bound by the lines x equals 1 here, and then the straight line and the curve. So this area is shaded here. So I initially thought that we could just find the area of this big triangle by finding the x-intercept here, and then just subtract the area under the curve. But actually, the line starts on top of the curve and then it goes underneath the curve, so that would actually be quite annoying. So instead, let's just consider from 1 to 3, and let's just do the top function minus the bottom function. So the tangent minus f of x from 1 to 3 should give us this shaded area. So that means we're going to need to know the equation of the tangent so that we can integrate it. So let's find this point 3, f of 3. What was f? Let's copy f from above. F of 3. 3 minus 1 is 2. E to the negative 3. So that's 2 on e cubed. So this is the point 3, 2 on e cubed. We need the equation of the tangent, which means we're going to need the gradient at this point. So the gradient of the tangent is the gradient of the curve at this point because it's tangent at that point. So let's use f dash x that we found earlier. This here, let's copy that. That was f dash x. And we'll use that to find f dash 3. Which will be our gradient of our tangent at that point, where x equals 3. So we have 3 minus 2 is 1, e to the minus 3 equals negative 1 on e cubed. Okay, equation of the tangent is going to be y equals mx plus c, where m is negative 1 on e cubed, x plus c, at this point. So we'll sub in 2 on e cubed, 2 on e cubed is equal to our gradient times the x value of 3. 2 on e cubed equals negative 3 on e cubed plus c. So c equals 5 on e cubed. C equals 5 on e cubed. Therefore, y, or g of x is what we're calling our tangent, is equal to our gradient, which is at this point is negative 1 on e cubed, x plus 5 on e cubed. And we're finding that so that we can integrate the tangent minus the curve to find the area between them. Now, when it comes to integrating the curve, we're going to use this recognition that they kind of guide us towards here. So if the derivative of this is equal to the curve, then the antiderivative of the curve is equal to this. So we can say using the antiderivative of f of x dx equals negative x e to the negative x plus c. We're going to have the area, the shaded area, is equal to the integral of the top curve, which is our tangent, negative 1 on e cubed, x plus 5 on e cubed dx, and then minus the integral of f of x, which we know is this. let's not forget our terminals. From 1 to 3 we're doing this. So 1 to 3 of f of x dx. Okay, let's find the antiderivative of this. So we're going to raise this x to the power of 1. We're going to raise that to the power of 2, divide by the new power of 2. So we're going to have negative 1 on 2e cubed x squared. And then plus 5 on e cubed x. 1 to 3. Minus, and then as we said before, via recognition, the antiderivative of this is this. Negative x e to the negative x from 1 to 3. And we've got a minus, so let's change that to a plus and cancel that out, which should make the substitution a bit easier. Subbing in 3 and then 1. So subbing in 3 here, 3 squared is 9, so let's make that 9. And then 3 here, 5 times 3 is so 15 over e cubed. Looks like we might have to find a lowest common denominator in a sec. But first, let's sub in this 1. Subbing in the 3 and the 1 into this. One on e. Okay, we've got negative 9 on 2e cubed, and then minus 1 on 2e cubed is going to be, well, that's a plus, that's minus 8 on 2e cubed, which becomes minus 4 on e cubed. Plus 15 on e cubed. Plus, we've taken care of that, so minus 5 on e cubed. Plus 3 on e cubed. And then minus 1 on e. Okay, so this is 11 on e cubed, 6 on e cubed, 9 on e cubed, minus 1 on e. I'm not going to bother finding a common denominator here, let's just leave it like that. Square units. This does look positive at least, so there was so much working out substitution to do here that it's very easy to make a mistake. So hopefully I didn't. So yeah, just take your time, be careful. But I think that is it. Alright, so that is the 2024 Northern Hemisphere Exam 1 for methods. Hopefully it helped. If I made any mistakes or if you have any questions about anything, just leave them in the comments.